Okay, ladies and gentlemen, welcome to this morning's panel discussion on automotive reliability and testing. Okay. As the number of sensors in cars grows from around 1.7 to over 8 in the next 5 years, the need for greater reliability in testing grows exponentially. This panel is going to discuss current practices and how they may evolve in the future. I'm delighted to be joined by Chris Palin from HumiSeal, to my extreme left, and David Greenmail from HumiSeal, or Chase Corporation, and of course Richard Boyle from Henkel. So welcome, gentlemen. Thank you for joining us today. My first question is that current testing parameters for automotive products are usually minus 42 degrees C to 150 degrees C. There are some requests to expand this range. Do you think this is really necessary? I'll start with you, Chris.
Well, I think a lot of people are still actually testing below that.
Okay.
I think the 150 is probably the maximum right now. Mm-hmm. Is there a need to go beyond? I think 150 is probably sufficient right now, but it's the number of thermal cycles that is the issue. Right now, around about 1,000. A lot of Japanese manufacturers are up at 3,000 cycles, thermal shock cycles, and that's where things start to get difficult. And right now, I think it's a destructive test rather than a test that anyone will pass.
Right. Okay. So you're saying that the Japanese standards are 3,000 versus the standards over here in Europe and US where it's 1,000 cycles.
Yeah, correct.
Yeah. Okay. Would you share that opinion, David?
Yes, I think so, because with the advent of electric vehicles, the voltages are increasing, therefore, and the current's increasing. You know, we're getting drives that are taking something like 60 amps. So you're generating a lot of high temperature within the control units. Right. So I fully support what Chris said.
Okay. Richard, you were saying, in fact, earlier, just before we came on stage, that the current was a problem.
It is, because that's what generates the heat, that's what generates the power, that's what gives you that perfect storm, if you like, to create the defects that you're looking to do. The higher the current, the higher the ampage, the more risk you have with the generation of the heat, and because you have the power there, that you can then grow the dendrites, you can have that ionic chemistry effect. What you've got to take into account as well is that even in the automotive industry, the components, the tracks are becoming smaller, closer together. Mm-hmm. So you are, if you like, emphasizing the potential for the current leakage, for the growth across those tracks. If the tracks of today are 20% or 20 times closer together than they were even 5 years ago, you're exponentially increasing that risk.
Of course. Yeah. No, I agree. You also mentioned that with these autonomous vehicles that are coming down, they're going to be operating at 48 volts as opposed to 12. What effect's that going to have?
Generally, I've always liked to say it's not the volts that kill you, it's the amps. But by running at the higher voltage, you are, again, moving further and further away from the standard test criteria that we're looking at. Most of the testing that is being carried out in the industry now is still running at 12 volts or 24 volts, maybe up to 100 volts for a single test. Mm-hmm. But very few people are actually running at the voltage, the current that is happening in real life. And the test packages we have don't simulate what's happening in real life either. And I agree 100% with what the others have said as well about the number of cycles that we're looking at. Mm-hmm. But also, it's not only, as we said earlier, it's not only looking at the single product that is on that particular electronic device. It's the compatibility with all of the things that are going on. Right. What's happened in the manufacture of the component? What's happening in the manufacture of the PCB, the printed wire board? Yeah. What's happening with the chemistry, not only from the materials to fix those components to the PCB, but then other materials we add to it, an underfill, a glob top, a conformal coating. Yeah. All of them have their own chemistries, and all of those can react together to create some very, very exciting outcomes.
Right. Well, I mean, you're obviously referring to CTE mismatches and things like this.
Absolutely.
Yeah, which, we really need to get a better understanding of, especially when we work into these smaller geometries. How much do you think this problem, there is a big problem of really standards just not keeping up with manufacturing and the pace of change?
Yeah, I think that's a big problem. The speed of change of current standards, IEC, IPC, etc., is slow.
Yeah.
I think there needs to be more discussion with industry, and as Richard says, with current requirements, voltage, spacing, and also package types. More BGAs in vehicles now.
Yeah.
5-10 years ago, no BGAs.
Yeah.
We're almost looking at military technology in vehicles today. What was in military 10 years ago is now in vehicles.
Standard in vehicles, yeah.
It's a big change.
Yeah, definitely. As the number of sensors and devices increases under the hood, of course, the competition for space is likely to increase, driving further miniaturization. What increased risks and challenges will this bring? I know that Richard touched on some of them, but I mean, maybe you could pick up on that, David.
Yeah, one of the things that we find is that we're one of the last, conformal coding is one of the last processes to go down on the board.
Yeah.
So we have to contend with everything that's gone on before, as Richard was saying earlier. And one of the things we're finding these days is that the reduced conductor spacing, the reduced conductor size, combined with lead-free, combined with the residues that are left, probably vitrified flux. When you start the 1,000 cycles to 3,000 cycles, you're getting mismatches, as we were saying earlier, of coefficients of thermal expansion, and that can lead to some very nasty effects.
Yeah.
And a storm could come, as you said, Richard.
Absolutely, and I mean that's not only an effect that occurs at the surface of the board. There's a lot of things that are happening nowadays in the 4, 5, 6, 7, 12 layers that people have in their automotive PCBs now as well. And I think one of the biggest issues, one of the biggest conversations I currently have with some of our customers is they still look at selective coating as a way to protect boards.
Right.
And the problem with that is that a standard FR4 board, a lot of the moisture doesn't come in from the top or the bottom, it comes in from the sides.
Right.
Or from through hole or from plated test points or things like that. And they don't look at that as an area to protect.
Right.
And that opens it up to, you can have the best combination of products in the world, but if you've got moisture coming into the board
From the side.
from the sides, you've opened up a lovely chemical soup there.
Yeah, absolutely. Well, one of the things that's always miffed me a bit is that 80% of the people that conformally coat don't clean before they coat, and they trap all this rubbish underneath, and they think they're going to get away with it. I mean, isn't it common sense?
I think 80% is probably an underestimation.
I mean, but isn't it just common sense to clean the board and get rid of any contaminants that are there before you trap it with some conformal coating?
Well, I think really you have two choices: you clean or you test. If you absolutely test the compatibility of every chemistry that's on the board, you're probably going to be okay. If you clean it 100%, as close as you can, then you're probably going to be okay. If you just take a set of materials that work or function in manufacture, solder resist, you buy some conformal coating and you use it, you don't know. I think that you don't know is the problem.
Yeah.
And to add to that, when I first came into this industry, quite a few years ago now, everybody was cleaning. The military cleaned, automotive cleaned, and now we've gone to lead-free. But in those 38 plus years, the conductor spacing has come down. We've gone from through-hole technology to surface mount. It's a different game now.
Yeah.
And I think that's why a lot of the automotive industry are now writing their own test specs. They're ignoring IPC, they're ignoring IEC. They're just not keeping up, as we were saying earlier.
Oh, I think the products are coming to market quicker than these standards can keep up with. That's the problem. Richard, I mean, do you think harsh environments bring an added risk of creep and migration? I mean, I guess.
Yes, definitely. We were touching on the point earlier that the standard test, the standard criteria is up to 150, and I agree with what Chris was saying, that at the moment that's probably okay. But we see more and more people want to not only test at minus 40 plus 150, but they want to have a dynamic test throughout the process. So instead of the test lasting for 7 days, we're now running 6-week tests where we will change dramatically not only the humidity, the temperature, but also chuck in a little bit of thermal shock halfway through the test, and also do some trips up to 170, 175 to see what effect that has. And I agree that unfortunately what's happening is that we are coming up with lots of different ways of testing now, and individual companies have their individual test specifications, and which is all good, which is all well and good, and I think it's important that we do that. But I think people are losing track of they're testing some things, not testing everything. And very few people actually go to the effort of putting everything together in one test. So you will test an individual product, not everything together.
But for an automotive application, which is a high reliability product, I mean, surely they're doing 100% testing, no? They're doing selective?
Some companies are testing more than others. It depends on what you're doing as well. If you're doing an airbag, if you're doing safety sensors, absolutely 100% testing is what's going on. Some other parts of the process, radar, that sort of thing, may not be doing 100% testing. But as we go more and more to autonomous vehicles, it only takes one of those small areas to fail, and the risk becomes quite high.
Right.
So I think the need for 100% testing of everything may become greater, and I think we might have to move back to the days where people were testing 100%. People were looking to perhaps clean more on areas where they feel there is a risk.
Yeah.
And people having to look at different solutions or different ways of design to manufacture to try and mitigate some of the potential issues that might come up.
Right. Right.
I would also like to add there that process control of the line is very important. Process validation, but also cleanliness testing at the end of the line, especially before conformal coating.
Yeah.
And that, I agree with Richard, should be probably around 100%. There's a lot of good equipment out there these days that can do that.
Right.
And if you do that, then you know that you're not putting the coating on top of a nasty contaminant.
So what would you recommend is the most effective cleanliness testing method?
The one that works. The one that works.
The one that works, absolutely. Absolutely.
I knew you had a view on this. This is why I was asking.
Certainly the good old Ionic contamination testing, I think that's a good process control tool. SIR is a good validation tool.
Yeah.
And both of those are readily available. The levels for ionic contamination have now been just revised by IBC, which I think is an excellent idea.
Yeah.
Years ago, I was always quoting when surface mount came in, 0.5 micrograms per square centimetre of sodium chloride equivalent. That's now becoming more and more available.
Right. Right.
I think, unfortunately, there is a risk also with looking at the standard ionic contamination process that we have out there, which looks at perhaps the whole board or a large area, and a lot of these ionics are trapped under particular components.
Yeah.
So it may be a requirement that you need to have some sort of selective ionic coating. One of the things that I've done with customers in the past is if they want to know exactly what's going on under a BGA, under a QFN, under a large area product, is take 10 of those boards, rip off those components, put them in a bag, do an ionic test only on those components. And you can see a massive difference in ionic contamination between that and the whole board.
Really? Okay. What about the different cleaning methods, Chris? I mean, a lot of people are doing cleaning, are using aqueous cleaning, but there's a lot more people starting to look at plasma cleaning and this type of thing.
Yeah, it's kind of interesting actually, because one thing we're interested in is adhesion to the surface, especially when you've cycled a unit for 1,000, 2,000 cycles.
Yeah.
One of the important things is the stuff still stuck to the surface? And quite often it won't be. So plasma cleaning is very interesting because it affects the surface energy immediately. So it raises the surface energy and gives better adhesion, better wetting of the coatings, etc. So, you know, low surface energy is like trying to paint the inside of a frying pan, a non-stick frying pan. It doesn't work. But if you're painting something, you know, a standard wall or whatever, then it's going to stick and it's going to stay there. So,
Right.
So yeah, and inline plasma machines, they're interesting.
Yeah, and there's a couple of systems here at the show that are actually doing plasma in air as well, not even under vacuum. So it's becoming an interesting area. What other technologies and demands are we likely to see in the future with automotive electronics in particular?
Well, I would, as I said earlier, I think the introduction of electric vehicles, that's going to give us a new challenge. As Richard said, it's the autonomous vehicles. The control electronics of those have got to be reliable.
Yeah.
Otherwise, we're going to see a lot of nasty incidents on the roads. And to do that, the whole process has got to be checked. It's got to...
Well, a lot of people are going more towards introducing a lot more automation, because automation brings, unfortunately, higher quality, because it takes some of the human error out of it.
Automation's only as good as the person who programmed it.
Of course.
Or the person who
it's
did
got to be
it.
set up correctly.
I have been on a lot of process lines that are fully automated, have very little organic unit interaction.
Right.
And some of the stuff they're doing is... I always like to feel that with automation, as with some of the old test criteria we had, it enabled you to create the same defect continuously.
Well, okay, let me reword what I was saying. Automation brings repeatability.
Correct.
As long as you get it set up correctly in the first place.
That's a better way of looking at it. I think you know, the advantage with automation is it takes out some of the variants that we can introduce to it as human beings. I also know very well that operators like to play with buttons and tweak and change things for the better all the time, even if it comes out with a worse result. Automation takes some of that away, but it's understanding what it is you're creating and what it is you're producing is the key factor there. And that needs to be tested as well to ensure that that is still ongoing. And machines drift. Yep. Things happen. So you have to keep that monitored at all times.
Very true. Very true.
I mean, how about thinking about printed electronics? Why isn't the electronics printed into your door panel? It could be.
Absolutely. Well, I mean, that's been... Well, you know, I mean, printed electronics has been... you talking about 3D printed electronics? That's been around for a long time, but one of the reasons it's never really progressed that fast is because it's impossible to get these assemblies in such a planar mode to put a pick-and-place machine on them, to put components on them. That's been one of the drawbacks. There's a couple of companies at the show, actually, that are starting to address that very issue. But that has been the barrier to 3D printed circuit boards really taking off.
But, you know, as flexible circuits come along as well.
Yeah, yeah.
Wearable electronics, flexible displays, more display technology. Yeah. And also, I think one important thing is the intra-vehicle communications. All cars are going to talk to each other, which brings along a huge security risk, potentially.
Yeah, yeah. That's right, and that's been highlighted actually in a lot of the IoT stuff with consumer devices, people hacking into your fridge.
Exactly.
Like this. Or a very famous one we have in the United States is they have a video doorbell system, which is meant to be a security thing, but what they didn't tell you is that if you take the front off of the doorbell, it gives you the IP address of the house.
Exactly.
So anyway, on that, gentlemen, I'm going to end the discussion. I want to thank you very much for joining us. It's been a great debate. Chris Palin from HumiSeal, David Greenmail from Chase Corporation, and of course Richard Boyle from Henkel. Thank you, gentlemen. Thank you for joining us.
Thank you very much.
Oh, we have a question. 1 second. 1 second. Can we get a microphone, sir? 1 second.
Here we go.
My name is Danny from Israel. I would like to ask two questions. One regarding qualification of printed electronics. Can you describe what is done in this field? And the second, do you see any problems regarding soft errors?
What was the second one?
Regarding soft errors.
Soft errors.
Soft errors.
Okay, I'll handle the printed electronics one. As everyone said, printed electronics has been around for a very long time. I'm always surprised why, with the miniaturization of everything that we're building, why we don't do more printed electronics in the PCB. Laser trim capacitors, resistors, that sort of thing could be easily done. Printed electronics is becoming more and more widely used for flexible, for 3D, for wearable, for a lot of stuff in sensors and automation. The biggest issue with the printed electronics has always been, and I think always will be, the cleanliness and the handling and the processing of the area in which it's carried out in. And it's generally quite expensive. You're generally using silver-based products which are relatively expensive. And the negative to that is that everyone wants everything cheaper. So when you're trying to produce a marketable sensor for a car, a wearable device, anything like that, if you're having to buy a material to allow you to print that electronic structure, and that's costing you 2,000 to 3,000 euros a kilo, that is never going to be competitive with the traditional solder route, which is still around about the 60 to 70 euros a kilo. So it becomes very difficult to maximize, to grow the printed electronic range of products while the cost is still so high. There is a lot of development work in coating nickel, coating copper with silver to try and reduce the cost, but the cost is still going to be a little bit higher. And it's a chicken and egg situation. Without growing the amount of printed technology there, you're never going to get the price down. But you're never going to get the stuff to grow until you get the price down. So it works a little bit difficult with that. The second one, we're running a little bit late. Can we take that offline? Can we do that as a one-to-one? We'll be there. You can come and talk to us about that. Okay. If there's any other questions, can we do that as well? Can we do that? Maybe you can buy us a coffee, and we can do that later on. Okay.
Okay. Thank you very much, everybody, for taking part. And that ends our debate today.